So just doing a little review. Let's do electron configuration of selenium. Selenium is Se. Okay, and I want the full electron configuration, not the abbreviated electron configuration. So the full one. First of all, can you find selenium Se? Where's it at? And give it to me in terms of 2s, 3p. Where is it? 4p what? 4p4, right? If I'm looking at selenium, it's right here. So that's where 1, 2, 3, 4. P, 1, 2, 3, 4. Okay? So we're going to fill every orbital in order to get to 4p. If you like to use the squiggle, right, that chart to help you figure out the order that the orbitals go in, that's perfectly fine. Or if you like to just kind of go along the periodic table and see, here's 1s, 2s, 2p, 3s, 3p, 4s. Then what's that d orbital called? Is it 4d or 3d? 3d. Remember, they're shifted up one spot. So it does get listed after 4s.
Okay, so it's like, whenever you're reading whenever you're listening it out, you write it how it's
it goes right.
But you just put it
Yep.
Okay.
Yep. Yeah. And then what's the way that I can check my answer to make sure that I'm correct? I can check myself at the end of the problem. I can count up my electrons if I really wanted to, right? 2 plus 2 is 4, plus 6 is 10, plus 2 more is 12, 18, 20, 30, and 34 electrons. So how many is selenium supposed to have? 34, right? So that's a way you can check yourself if you feel like you need to. Okay? If you have an ion, that's a great question. If I was going to do an ion, let's say that I wanted to do selenium -2, because that's its normal charge. I would add 2 electrons to it. And so instead of being 4p4, it would end in 4p6. So I would not be able to tell the difference between the electron configuration of selenium -2 and krypton. They would look the same, right? There would be no way for me to tell if they both ended in 4p6. I would have no idea if I have the electron configuration of krypton or if I have the electron configuration of bromine -1. Or if I have the configuration of selenium -2, arsenic -3, right? There's no way for me to know. This is just talking about the number of electrons and their arrangement. Yeah, that's a great question. Okay, anything else?
You just add so you just add the 2 extra electrons to that?
Yeah,
if it would be the element itself. Does that make sense? Like on N. Does that make sense?
This one right here?
Yeah.
If
you had the -2, you just add it onto that last.
Yeah. Right? Because I would have 2 extra electrons. So if I was trying to get the configuration for Se -2, I have 2 extra electrons there, so I just add it on the end. And it might cause you even to go to the next orbital, right? It might cause you to do that.
On 4p6, and it's you have to add an extra 2. Would you add it on to 4p?
Nope, you would go then to 5s2. Yep. Okay. Okay. Very good. Tell me, identify this element for me. I'm going to put up the ground state or the neutral configuration of an element, and I want you to identify what element it is. Okay, so I want you to tell me what element that is. Identify the element based on the electron configuration. We're going to say it's neutral, right? I'm not giving you an ion here. I'm just giving you a neutral atom. What do we think? Palladium. Yep. PD. Palladium. PD. Were y'all guessing how I was supposed to be said? Palladium? No, I think it's palladium. I think it's palladium. Okay, do we feel a little bit better than we did yesterday with electron configurations? Or about the same?
Palladium.
All right, very good. Now we're going to start drawing the electron configuration. So we're going to do what's called orbital notation. So it's a different way for us to write out the electron configuration in what's called the orbital notation. So let's remind me really quickly before we get too far into this, how many electrons can be found in a single orbital? Orbitals can hold how many electrons? 2, right? And there might be different versions of p orbitals and d orbitals and f orbitals, but a single orbital can only hold 2 electrons. And so in this way, to annotate electron configurations, we draw orbitals with just a line, right? We give ourselves a line, and then if there are electrons present, they are represented as an arrow, okay? So an orbital that has a single electron would just have 1 arrow in it. And an orbital that has 2 electrons would have 2 arrows in it, okay? So an electron orbital that's empty obviously has no arrows in it, right? But that's how we would represent that. And in all reality, they're really represented by like a half-headed arrow like that, up and down. But I didn't know how to make the computer do that. So that's how they're really drawn, right? With a half kind of headed arrow.
Is that just the 2?
This is the 2. Yeah, sorry, I should put that down here, okay? A single arrow would look like that. When we put electrons into their orbitals, we always put the electron we put the first electron pointing upward, and I'll explain kind of why that is here in a little bit. But when we put our electrons in, the first one is always positive, and the second one is always negative in terms of what's called their spin. Okay, but the arrow that points up is always going to go in first. One that goes downward is going to go in second. Okay, but a single orbital is a single line. And then this would be the 2 electrons found in that orbital. Okay, so we need to, first of all, remember that electron configuration. When I ask you for electron configuration, that's when we do 1s2, 2s2, 2p6. But orbital notation is when we draw the arrows like this. So there's going to be 2 different categories of this that I'll ask you to annotate. Okay, so let's learn some rules about how we draw orbital notation. And the rules seem... I feel like they almost seem unnecessary, but it's a way for you to understand the pattern of how electrons go into orbitals, okay? So it's called Hund's rule, and Hund's rule says orbitals of equal energy are occupied by 1 electron before any orbital is occupied by a second electron. Okay, so let me kind of explain what that means. How many different types or how many versions of p orbitals did we say there are? They can hold a total of 6, but they each have 2, so there's 3 versions of p orbitals. So let's write that out. There's 3 versions of p orbitals, okay? And all the p orbitals have the same amount of energy. They are on the same energy level. So if I draw my 3 versions of p orbitals here, right, we just draw them as lines. And let's say that I needed to represent an element that was 3p4. 3p4. So I need to draw in 4 electrons. But I have to follow Hund's rule, and I can't just draw them in 1, 2, 3, 4, right? That's no good. What Hund's rule says is that orbitals of equal energy are each occupied by 1 electron before anyone gets a second electron. So when I put in my 4 electrons, it would go 1, 2, 3, and then 4, right? I have to fill an electron in each version of that p orbital before anyone gets a second one. Okay, that's the rule. I've got to put 1 in each before I go back and put in a second one. And I know that seems kind of redundant, but that's just the rule, right? We have to put an electron in each version of that p orbital before anyone gets a second one. Okay?
And the 4th one just goes back to the beginning.
Yep, we go back to the beginning, right? So we're going to go 1, 2, 3, and then we come back to the beginning for the 4th one, okay? Now, the second rule says here that all electrons in singly occupied orbitals, so anyone that has just 1 electron in it, has to have the same spin state. So we haven't talked about spin yet. Spin state for electrons, they either spin in the positive direction or the negative direction. And that's a little bit more intense than we need to get into just right now. But when 2 electrons are in an orbital together, one of them has to spin in the positive direction, one of them has to spin in the negative direction. If there's 2 of them in there. If there's only 1, like we said here, we're going to fill them all with the positive spin state first, then the second one is going to get the negative spin state. So the second one that goes in is going to be pointed downward. So we're going to fill them all with the same spin state first. Positive, positive, positive. And then the second one that goes in is going to get the opposite spin state. Okay, so we're going to fill them across and then come back with the second one. Okay, let's go ahead and try an example here with nitrogen. We're going to write out the electron configuration first, and then I'm going to show you how we're going to do it with orbital notation with the arrows, okay? So nitrogen's electron configuration, let's go ahead and write that out first. Okay, nitrogen is 1s2, 2s2, 2p what? 3. 2p3. Okay, so this is the electron configuration. Okay, now the orbital notation is what I'm going to draw next. That's our new topic for today. Orbital notation, right? Notation is just like a way to draw something. So orbital notation is going to be right here, and I'm going to draw the orbitals as their line. So the 1s orbital is just a single line because the s orbital, there's only one version of it, and it can hold how many electrons? 2. So here's my 1, 2. Then I'm going to go up an energy level and write 2s orbital. How many can it hold? 2. And then my 2p orbitals, we said there's 3 versions of them. So I'm going to write 2p down below those 3 orbitals. And I've got 3 electrons to put in. So am I going to put them in 1, 2, 3 like that? No. Nope. What's the rule? I've got to go all the way across before I can give anyone a second. But I only had 3 to put in. So do I just stop right there? Yep, that's it. Okay, so orbital notation, we're giving the same configuration, but we're drawing it out in more of a picture diagram than writing it out in our electron configuration.
Why do we only do one line for the 2s?
Because the s orbitals, there's only one version of an s orbital, right? The 1s orbital just has one thing, it's that circle. And it only fits 2 electrons, and that's how many an orbital can fit anyway. So we just have to draw one line for the s orbitals. Okay, p orbitals, there's 3 versions, so we draw 3 lines. How many lines and how many orbitals would we represent for a d orbital?
15.
D can hold a total of 10, so how many orbitals would I need to draw? 5. Good. Okay, very good. All right, let's try some more here.
What would you do if it was like a 3s?
So
Would you do the same? You would just write one line, right?
yeah, if it was 3s, I would go 1s, 2s, 2p, and then I would go 3s, just with one line like that.
Oh,
Okay? All right, so let's try boron. Boron is, I'm not going to write out the full electron configuration here. When I write orbital notation, all I do is, I know boron ends in 2p1, right? Would we agree with that? Is boron 2p1? So I'm just going to write out the end of the configuration to help me kind of remember. But then when I draw it, I'll have to draw all of them. So 1s, I fill its electrons. 2s, I fill its electrons. 2p, can I pick any line to put it on?
no.
Nope, I've got to start on that first one right there. 2p1, right? And I can count my electrons also to make sure I represented all of them. Boron is supposed to have 5, which is how many I drew. Okay, if it's helpful for you to write out the whole configuration, by all means do that, right? But once you get a little familiar with it, I don't think you'll need to write out all of them. Okay. Any questions with that? All right, why don't you try fluorine on your own, and then we're going to do a different one at the last to get a little bit tougher example here. So try fluorine on your own, and then we're going to scratch that last example and change it to something a little different. in the D block. So I want you to try nickel, Ni, and see what that one looks like.